Welcome to our FAULHABER Drive Time. In this video, I want to show a few tricks when dealing with high inertia and low friction. So I'm going to use the setup here and the relatively big disc, big at least compared to our motor here. Setup is an MC5005 SCO, can open version, and 3242 BX4 motor having the linear Hall sensors. And I'm going to use the big disc here, which has roughly a factor of 20 compared to the motor in the inertia. That's more or less like trying to pull your boat to the lake using your scooter. Starting might not be the problem, stopping might be. So let's see what we can do. I already configured the motor and can directly start with identifying the inertia here and then start the tuning. So let's switch to the motion manager again. Once again, the motor is already pre-configured here. So sensor system and motor type, and we can directly start identifying the inertia. That's done using the configure controller tool here. And of course, the two ways of entering inertia manually or identifying. If identification doesn't work for you, please give us an estimate about what you connected to the motor. But I'll first give the identification a try here. So let's start this. And the motor is moving. Actually, it's moving bigger distances now than with the small disc. But it finished the identification, and here's the summary. Again, the 30 for the inertia of the motor, but now a significant inertia for the disc, roughly a factor of 17 here compared to the motor. So this is a heavy load, and we get a completely different set of parameters here, transfer them to the controller and are finished. I don't need to save them right now because I'm directly going into the controller tuning window. And basically it's the same steps here. So first one step in speed response here. And it's not really nice, but let's check with the position loop. At least stable, but very slow. So same steps as with the small disc. Switch back to the velocity and try to increase the speed loop gain, but there isn't much headroom because with the high inertia, the corridor of gain that we can use is relatively narrow here. But anyways, I got this. And then I directly activate the feed forwards, sliding completely to the right here, and switch again to the position loop and then do one step here, one turn of the motor again, and that's fine, actually. Perfect following. I can even try to increase the gain here a little bit and check for stability. Yeah, it's working against my hand here, so it seems to be stable. Maybe once again the remark about the current range here. For acceleration, 3 times the nominal current of the motor is already used. When we want to have some headroom or to compensate for disturbance, it's a good idea to reduce the profile parameters a little bit here. So both of them, and the rule is roughly 1/3 of the acceleration should be the value of the deceleration. I expect perfect following once again, and that's what we see. Yeah, fine, but the peak current now is 2.5 times the nominal current. This should be sufficient to compensate for any unexpected disturbance. So we are fine here. And for the main effect of the big disc, I now directly save the parameter here and step out of this window here and use the motion cockpit and the graphical analysis to show you what's happening here. The default parameters for the graphical analysis are the actual values for position, velocity, and current. That's of course what we want to have here, and using the motion cockpit I can directly command different movements. So here, being in profile position mode, move to 0 position and then start the graphical analysis here. Well, it's a little fast here. Let's use a bigger range for the time here, so it's slower, and then command, let's say, 10,000 increments here. That's 2.5 turns of the motor, and yeah, it moved and moving back. Fine. But what I want to show you here is an additional effect. I need an additional signal in the graphical analysis, and therefore I need to open the configuration dialog here, and I want to add the motor supply voltage. I can use the filter here, motor supply voltage. Here is the motor supply voltage, and add it to the list of signals that we are supervising here. And once again, start moving. And now let's move 50,000 increments. Okay, here we are. I'll stop here, and then let's zoom into the movement here. And what we are seeing here is the red line is the position, that's fine. Green line is the speed, so accelerating and decelerating again. The orange one would be the current, and the blue line is the voltage. So what we see is it's decreasing a little bit in the beginning. That's because the power supply has a challenge to deliver the current, and in the end, when decelerating, we are going up a little bit. Okay, so far. Now let's move back to the 0 position and try again with 100,000 increments and start the logging here and do this again. And let's stop this, zoom into the movement and check the signals. And what we can see here is that now the supply voltage is significantly increasing during the deceleration phase, because we are delivering kinetic energy back into the electric system. And while you want to have this with your car, because you got a battery which can deal with the energy flowing back, the power supply here is a standard industrial power supply, and we tested a lot of them. Many of them simply switch off if you got such a voltage peak back. And therefore, we have to somehow deal with the voltage here. Let me move back and once again increase the range of the movement here. Okay, here we are. Zoom into it. And what we now see is on top of here there are these dents in the voltage, and that is because first of all I can observe the speed is now pretty high. It's about the nominal speed of the motor that's reached for a short time, and when now decelerating with the big disc, there's a lot of energy coming back and the voltage is increasing here, and the dents here are coming from my braking chopper. So there's a additional electronics component that I mounted in my system setup here, which is kicking in and burning the energy in an internal resistor. If I wouldn't do so, I can change the behavior here. Then let's see what's going to happen, because what we can see here, the braking chopper is kicking in at roughly about 28 volt. If you remember, the default setting for the voltage threshold during initial configuration of the motor was plus 15% compared to the nominal voltage. So nominal was 24 volt, the threshold would be 27.5. I can change this using the drive functions window, and what I did before capturing the video here was manually increasing the value to 30 volt, but now going back to the 27.5 and send that one and close the window. And when I now go back the same distance, okay, here we are. So let's again zoom into that one here. And what we can see now is there are no dents in the voltage here. It is limited because the internal control will try to limit the excess voltage here to the threshold that we configured, so the 27.5 volt. But there is additional a time limit for which this excess voltage is allowed, and the default value is 200 milliseconds. And now to decelerate the big disk here, 200 milliseconds isn't sufficient. And then we produce an error, and the control and the complete power stage is switched off. And so when we have to deal with the big inertia here, we either have to add the braking chopper, or we optimize the parameters of the overvoltage control. So that's been the threshold here. And then there is the delay time. Let's try with a bigger one, 500 milliseconds, and can send that one, close, and try again. And okay, and we are still in control now. So the movement finished, and when I zoom into the movement here, we can see the drive moving at its nominal speed for quite a time, and then here's the deceleration phase, and the voltage is going up to these 27.5 volt, and we can even use some measurement in here. And okay, that's a little more than the 500 milliseconds that I configured, but the actual threshold is up here, and up here the 500 might have been sufficient. Yeah, very close, but sufficient. Okay, so far about what we have to do with big inertias. Be careful, because your drive might switch off, or you might get overvoltage in your system. So far about dealing with high inertia and low friction. The built-in winder protection allows us to deal even with this relatively big disk here. Like I mentioned in the beginning, pulling your boat with the scooter might give you a challenge when trying to stop. And so what we had to do here is either use the braking chopper or allow for temporary overvoltage. Alternatively, you could of course always use a gearhead to adapt the inertia of the load to the inertia of the motor. That's like using a tractor for actually slipping the boat. In the next video, I'll then use both of them and will explain how to deal with distortion in the motor control. So please check back with our channel, and if you've got any questions in between, contact our local sales team or our MC support team. You might as well leave a comment below the video. Thanks for watching, and bye.